So, good afternoon, everybody. Welcome to today's NCCAV seminar. Today, we are delighted to have Dr. Shoaib Samandar and Tanmi Das as the speaker. Dr. Tanmi Das is having his PhD in civil engineering received from North Carolina State University. He's specializing in applying AI to traffic flow theory. His research centers on car following dynamics and safety evaluation of autonomous vehicles, navigating in mixed traffic control with connected autonomous vehicles and traditional vehicles. Currently, he is serving as a highway safety analyst at VHB in Raleigh. At the same time, he's also having a role as a research assistant scholar at Institute for Transportation Research and Education at North Carolina State University. We're also having Dr. Shoaib Samandar, who is a research scholar at NC State A3 Institute. He's specialized in intelligent transportation systems, and his research focuses on integration of artificial intelligence in transportation systems and development of connected autonomous vehicles. His research contributions in these domains are documented in over dozens of peer-reviewed publications. He's also the PI from the CSA in NCCAV Center, and we have been delighted to have been working with him as a part of NCCAV Center. And today's talk is on regularized stacked LSTM car following model for autonomous vehicle in mixed traffic setups. So before we start, I would also like to thank the sponsors of the NCCAV Center, which is NC Duty. Also, I would like to acknowledge the support from industrial partners, Google, Verizon, Volvo, RTI, and Intel. With that, I'll pass it to the speakers.
Thank you, Dr. Karimuddini. I think, Tanmi, we need to share. Can you go ahead and share the slides? I'm not sure if I'm the host or you're the host, but we should be able to go ahead and share that.
Let me know when you see the slides.
Very good.
So is it the full screen mode or it is like the?
It's good.
Okay, awesome.
All right. Good afternoon, everyone. Thank you, Dr. Karimuddini, for the introduction. We are delighted to be here to present our latest research at NC State University. We'll be diving into a cutting-edge topic at the intersection of transportation engineering and AI. The topic, as Dr. Karimuddini mentioned, is regularized stack LSTM for autonomous vehicle car following models. As he mentioned, this work has been part of the STRIDE UTC Center. The majority of the developments have been done within a project that dealt with building car following models for autonomous vehicles, but it also intersects with the project that we have at NCCAV, which I'm leading on NC State side. Can we go to the next slide, Tanmi? All right, let's take a look at our roadmap for today's session. The outline is as follows. First, we will set the stage with the introduction to our topic. We'll discuss the context and significance of our research and the broader landscape of AVs and traffic flow theory. We will then identify and discuss the current car following model limitations, addressing the gaps that our research aims to fill, particularly in the realm of a mixed traffic environment where human-driven and autonomous vehicles coexist. Following that, we will dive into the research methodology, discussing the real-world collected AV data set that we have used, and that serves as the foundation for our model development and validation. Next, we will dissect the architecture and functioning of the LSTM models. We will elaborate on why this form of deep learning is particularly suited to the task at hand, and we will share some key findings. Moving forward, we will touch upon model explainability, a critical aspect of AI that ensures the models that we develop are not just black boxes, but rather transparent systems whose reasoning can be understood and trusted. And finally, we will wrap up with our conclusions, summarizing the insights that we have gained and discussing the next step for this line of research. Next slide, please. Let's start with the fundamental concept of car following, which is central to our discussion here today. Car following is the operational behavior of a driver or an autonomous system while they follow another vehicle. It's the process that dictates how a vehicle responds to the speed, the distance, and actions of the vehicle that's in front of it. The top image that we have here represents an abstracted view of car following in a relatively controlled environment where variables can be easily measured and behaviors predicted. However, the bottom image captures the essence of real-world driving scenario. Here, a driver's perspective is filled with complexities. You have varying vehicle behaviors, diverse road conditions, and unforeseen events. In this slide that we are observing at the moment, we delve a little bit deeper into the types of car following model that forms the basis of our analysis. Broadly speaking, car following models can be categorized into two types: analytical models and data-driven models. On the left side, you see under analytical models an equation representing the Gibbs model. This is a time continuous model that predicts a vehicle's next position based on its current speed, the speed of the car in front of it, and a safe stopping distance. Such models are usually derived from observed driver behavior and the physics of motion, providing a theoretical framework for understanding car following dynamics. Also, these models are essential for their explanatory power and their foundation, and they are the foundation in traffic flow theory. Moving to the right, we have data-driven models. These are predicted using real-world data, statistical machine learning methods to predict vehicle behavior. Unlike analytical models, the data-driven models do not assume a predefined relationship between different variables. They learn majority of these relationships directly from the data. And our research that we're presenting today focuses on leveraging the strengths of data-driven models using LSTM networks to handle the nonlinear and temporal complexities and aspects of car following behavior in the mixed traffic conditions. This, as Tanmay will come to it, involves training our models on extensive data sets collected from real-world driving data sets. The slide that you are seeing right now provides highlights on the gaps that we see from the literature. Through an extensive literature review, we have identified that while the LSTM data-driven approach is widely used in the literature, there's a noticeable gap. Specifically, none of the existing AV car following models have incorporated response time within the context of mixed traffic scenarios. Response time is a critical component in understanding vehicle dynamics and driver behavior, particularly in situations where autonomous vehicle must interact with human-driven vehicles. The statement that we have on the left indicates that while the use of LSTM for analyzing traffic data is not new, its application has been limited in scope. Also, the bullet point that we have on the right, we address a critical point, which is none of the existing AV car following models have used real-world mixed traffic data, at least not until the time period where we worked on this. This is, we believe, a significant oversight as real-world data provides the nuances and complexities that are essential for developing robust and reliable car following models. Our research is taking a stab in that direction and fills this gap by incorporating real-world mixed traffic data and response time into the LSTM models. As a result, providing a more comprehensive and realistic understanding of car following behavior in mixed traffic. Next slide, please. Let's now focus on the drawbacks of the analytical models, specifically in the context of AVs. On the top left, we see a complex equation that represents an analytical car following model. This model predicts a following vehicle's acceleration based on a set of parameters like the relative speed and spacing between the vehicles. However, the scatter plot below that we see, which compares predicted versus observed acceleration for the ACC model, illustrates a key limitation, which is one of the biggest limitations of these analytical models. The blue dots represent observed data points, and the red line indicates the prediction made by the ACC model. That the mathematical formulation is up top. You can clearly see a discrepancy between the two. And this highlights the model's inability to capture the variability present in real-world driving conditions. This is a critical issue because accurate acceleration prediction is very important and fundamental for ensuring the safety and efficiency of AVs in the context of mixed traffic. Next slide, please. In this slide, we examine the gap from experiments focusing on response time, which is a pivotal aspect of car following behavior. Yet a lot of the models often overlook this during model development. Our empirical work has estimated response time of AVs operating in mixed traffic. It has been noted somewhere else, which the reference is provided at the bottom of the slide. The bullet points below the graph emphasizes two distinct points. First, AVs have significantly higher response time compared to TVs. This information or insight is vital for calibrating car following models to reflect the different capabilities and behaviors of AVs versus human-driven vehicles. Second, existing data-driven car following models do not consider response time as an input. We believe this highlights a significant gap in current models, which tend to ignore the temporal dynamics of AV's reaction in traffic. Next slide, please. This slide encapsulates the motivation behind our research, providing the driving force that led us to pursue this particular avenue of inquiry. First, we acknowledge that existing car following models for AVs have predominantly been developed and tested under homogenous traffic scenarios. These models often assume a uniform type of vehicle, which does not reflect the complexity of real-world traffic, where autonomous and non-autonomous vehicles, which we call them traditional vehicles, share the road. Second, we address the analytical model's limitation in predicting high acceleration and deceleration values. Traditional models struggle to accurately predict these critical metrics, especially in emergency or unexpected driving scenarios, which are places where AVs and their technology can have significant safety benefits. The third point emphasizes that existing data-driven car following do not really consider response time as an input. This oversight can lead to models that are out of sync with the real-world reaction of AVs, resulting in a less accurate representation of their behavior. We believe that a reasonable solution, we also show this by the end of this presentation, will be use of LSTM networks, which can include multiple features such as response time. This approach can better predict extreme acceleration, deceleration envelopes, and is capable of accounting for the varied composition of traffic. Next slide, please. In this slide, we focus on the data set that we used in our analysis, the OpenACC data set. OpenACC data set is a publicly available data set that was collected across various locations in Europe. This provides various perspectives of driving conditions and behaviors. The OpenACC data set is remarkable not just for its trajectory data, which includes the precise measurement of vehicle positions over time, but it also provides supplementary information. This includes details such as engine type, make, and model of each vehicle involved in the study. We believe that such granularity allows us to understand the impact of different vehicle characteristics on car following behavior. Additionally, the data set collected has a total of 27 different vehicle models, different version of Teslas, Volvos, Kias, 27 different types of vehicles. That this ensures a wide range of driving dynamics and technological features. This diversity in the number of vehicles and types of vehicles is crucial for the generalizability of findings. It basically ensures that the models developed are not just tailored to a specific type of vehicle or model of vehicle or make of vehicle, but are robust across the heterogeneity of the modern vehicle fleets. Next slide, please.
Yeah.
Tanmay will take this over. Go ahead, Tanmay.
Yeah, thanks, Dr. Samandar, for creating the perfect flow to describe about the training data set. So as Dr. Samandar said that we have used OpenACC database for the model. And as we are developing like learning-based models, like neural net models, it's pretty important that what type of data we are using for the training of the data for the model. Because neural nets, like learning-based models, will learn from the data set itself. How the data is, how many variation in the data is there, is perfectly determinate factor for the model performance. So I'll give you a moment to understand the data set. So this is actually a Violin plot of the training data set about the input that we have used for the model generation, or I can say model training. I'll just give a moment to look at the graph on the left. So as I was mentioning, the data set is pretty extensive with 12 pairs of vehicles collected at different highways and test tracks. And it also comprises vehicles from different manufacturers. And this is the two type of car following scenarios it comprised. First, when the autonomous vehicle was following an autonomous vehicle, and the second, when the autonomous vehicle was following a traditional vehicle. Now, as I said that the learning-based algorithms needs to learn from the training data set. So the training data set, our training data set have different driving scenarios that can happen while a vehicle will be driving on the roads. For example, it has a cruising driving scenario. That means the vehicle will not change its speed. Speed drop from oscillating state with certain like deceleration, speed drop from equilibrium state, high acceleration, like stop and start, like a signal, traffic signal scenario, stop and go, like a phantom jam scenario. So these are the scenarios that have been included in the training data set so that the model can learn from those scenarios and actually can predict those intricate relations between the scenarios and the car following dynamics. So this is the taste data set. I will not go very deep about that. It is a similar Violin plot about the taste data set. The taste data set had two types of two vehicles from two different manufacturers for the AVs. The first one was Tesla with a response time of 1.6 seconds, and the second one was from Audi. It has a response time of 1.8 seconds. So let's talk about the method we have followed for the whole model training, testing, and validation. So as Dr. Samandar mentioned about the data set, after having the data set in our hand, we actually divide the data set as I've shown the train testing validation. Then we developed LSTM model. In the title of the presentation, we mentioned about only the regularized LSTM model, but we actually didn't come to the conclusion like right away. We tested different LSTM models as well, different specialized LSTM models to find which model is doing better in terms of the data set and prediction, everything. So on the LSTM model part, we will show those models that have been used to like test which model is doing good. After that, we did the model evaluation using the test data. But before doing the model evaluation, we did the hyperparameter tuning, and it was an iterative process, trial and error, so that we find the best performance out of the model. After that, we actually proposed a model and compared those models to find which model is doing the best in terms of predicting the acceleration of autonomous vehicles. So first, we have used the regularized stat long short-term memory-based LSTM model. So on the left side of the slide, you can see a normal LSTM cell. But we know that the learning-based algorithms have an issue with overfitting. So we actually modified the model by adding the regularization term into the LSTM model. As you can see from the equation we have presented here. I will not go deep into this equation. I will definitely answer any questions if it comes in the question answer session about these equations. So after that, we actually defined the structure of the model. Like it was a stacked LSTM. So that means it has different stacking from one on top of another. So it has 3 layers, as well as with the regularization term, you can see the structure of the LSTM model on the left side. On the right side, on the right corner, bottom corner, you can see the hyperparameter tuning results, the variables range that we have used for the hyperparameter tuning, and as well as the selected variables that we have come from the cross validation, and it was a glitch set method for the hyperparameter tuning process. So this is one LSTM model that we have used for testing. The second one that we have used for testing is actually people LSTM model. So we have used people LSTM model recognizing its suitability. So because the candidate cell tell of the people LSTM model gives is an observation of the different cell states, making the prediction actually very good in terms of the long-term sequencing. So you can see also on the left side the difference between the previous LSTM and this one. So you can see the people connections within the cell structure. Yeah, and these are the equations. These are the modifications over the natural. So the equation only shows the modifications for the P4 LSTM. I am not showing the input or forget get because those are like pretty similar for the all LSTM models. The modifications that have been done for the P4 are only shown here. On the right, on the right corner, bottom corner, we can see again the hyperparameter tuning. I have done the red bold 0.005 to show the variation or the change from the previous one of the value, which is the learning rate. For this one, the model performed best when the learning rate was that value. After that, we tested another LSTM, which is actually LSTM with attention. So why we use that? We know the car following dynamics, the acceleration prediction and everything is actually pretty complex scenarios. And when it is under the mixed traffic with human-driven vehicles, it adds to the complexity. So we actually choose the LSTM model with attention because we know that attention mechanism doesn't give similar weights to every scenario. Rather, it gives varying weights to scenarios that it needs complexity. It's a very complex scenario. It gives different weights so that it learns from the important part itself. Again, the equations shows the difference from the basic LSTM model. I'll not go deep into those. I'll definitely answer any questions when it comes in the question answer session. Again, for the hyperparameter tuning, fortunately, the from the regularized LSTM model, there was a change in the parameter value for the hyperparameter tuning. So that actually solves the hyperparameter tuning for the LSTM with attention. So these 3 were like a specialized LSTM model, but we don't want to like only focus on the specialized one. We also wanted to see whether the less complex models like the gated recurrent unit, how they are performing that. So we have also added the gated recurrent unit model for our comparison purpose, like which model is actually doing better in terms of acceleration prediction while the autonomous vehicles are operating in the mixed traffic. Now, this actually gives a very brief summary of what I've said in the last slides. So I'll not go detail about them, just to show which models we have actually used for the comparison. So the first one was the regularized LSTM model. Then we went to the P4 LSTM model. Then we went to the LSTM attention, and last was the gated recurrent unit. So these are the models. It has some benefits. That's why we actually used for the car following prediction. Now we are going to investigate that which model is actually doing better in terms of prediction, the acceleration behavior. So let's go to the findings first, as well as evaluation. So first slide here is an evaluation of LSTM, RS-LSTM acceleration prediction. Before going into the values, let's just describe what these graphs mean. So on the left side of this graph, you see the predicted acceleration versus observed acceleration. So it is a scatter plot. The red dotted line is the regression line, the regression slope line. how the predicted and the observed acceleration is actually showing the trend. And the black dotted line shows the 45-degree angle. That means if the model is predicting perfectly, the red line should have been on the top of the black one. So on the right side, this one actually shows the observed acceleration. That means the observed value of the acceleration based on which the model is actually like trying to predict the value. So, and this shows the difference between the observed acceleration and the predicted acceleration. It is the error plotted. Both of the plots are actually plotted over the time. Now we see the RMSE value is 0.114. We'll discuss about this RMSE value with other comparison in the next slides. Now this actually shows the performance of the P4 LSTM model. Again, the same pattern of the slides, the observed versus predicted, the slope and everything. So to compare, you can see the slope value for the RS-LSTM was 0.87, and the P4 is actually a bit reduced again, but it is doing fantastic job while predicting the acceleration and for predicting the observed acceleration. But again, it is not better than the RS-LSTM. Now going to the attention mechanism, you can see the slope value is actually decreased. Also the deviation or the peaks in the prediction are also a bit increased, as well as the overall RMSE also got a bit increased. So we can definitely say that at least for these data, the LSTM with attention is not doing like huge better than the RS-LSTM and the P4 LSTM. For last but not the least, we also did the same for the gated recurrent unit, which has got an RMSE value of 0.129, which is good. Again, good. In fact, the second best, but not as good as the RS-LSTM. So again, while we are using RMSE value, there's a weakness of RMSE value. When we're saying RMSE value, it depends on the data set itself. Now, if you see the graph of any, you can see a large portion of the data set actually is accumulated within the zero acceleration range. There is very few points on the high acceleration and high deceleration zones. But the basic thing is that we also need a model which can predict those. So how we come up with that solution? We tried like bar-based RMSE, like small bar-based RMSE comparison. So to describe what the graph is, it is actually showing different bars of acceleration. For example, this one means -4 meter per second to -2 meter per second, and the RMSE values corresponding about the prediction of the 4 models that we have shown here. Similarly, for -2 to -1, and all the brackets and all the different zones of acceleration that we have used for comparison. So from this graph, it is pretty visible that the proposed models, the LSTM models, were very good in terms of like predicting the high acceleration, high deceleration. However, we have also seen that the models were performed better in predicting the high deceleration rather than predicting the high acceleration, which is actually a good future research that we are now trying to solve. Again, we have seen that among these 4 models, the RS-LSTM model performed not only in terms of the overall RMSE as well as segment-wise RMSE. So that's why, based on this comparison, we selected that, okay, we will go with the regularized stack model for the analysis part. So what analysis? When we started the slide, we showed the motivation was we will develop a model that will perform better than the analytical one, and obviously show the limitations of the analytical model and the development over that. So next, this slide we have already seen in the previous one. Again, I will just show the limitations of the analytical model. As you can see, for the high acceleration and high deceleration zones, the model is not predicting well. Though we actually calibrated the model, we use genetic algorithm for the calibration using the data set that we have used for the training of the LSTM model, and use those parameters to find what the values are. So it is visible the analytical models have some issues, and the analytical model that we are now showing is the model developed by Schledova, California Park Berkeley Lab, for actually autonomous vehicles. The name of the model is the SSE model, and it is pretty quite commonly used for the autonomous vehicles car following. Now, how the RS-LSTM model is actually overcoming the limitations. Again, you have seen the slides beforehand, but now you can see the comparison. So same data set, same thing. But as you can see, the RS-LSTM model is predicting the high acceleration, high deceleration pretty well, where the analytical model, the Schleiermacher model, is actually have some limitations as for predicting those high acceleration, high deceleration. Also, if you see the slope value, so it's a very contrast, like it's 0.39 and this 0.87. So obviously, the all other LSTM models are doing better than the other. But the RS-LSTM model, as it performed better among those four, obviously it's performing better than the analytical model here. But we don't actually stop here. We also compared at different ranges of acceleration as we did for the whole LSTM model. Again, the results are very visible to everyone. Like for each regime, like each acceleration regime, the proposed model, the regularized stacked LSTM, performed better than the analytical, which was our motivation for developing the new one. Now, let's come to the model explainability. Dr. Samandar will take over the presentation and explain the model.
Thank you, Dr. Das. In this particular slide that we see here, we used SHAP, which is Shapley additive explanation, to decipher the contributions of each feature to the model's output. The SHAP value plot that's shown here provides a visual representation of the impact of different features that is available in the model's prediction. Each dot represents the SHAP value for a feature and a data point. Also coming to the color, I believe blue is for low and red is for high, and its location on the x-axis shows the impact on the model output, with the left side indicating a push towards lower values and the right side indicating a push towards higher values. We observed several key insights from this plot. First, the acceleration of leader feature has a significant positive effect on the model's output. As the leading vehicle accelerates, the model also predicts an increase in acceleration for the following vehicle. Second, the relative speed feature has a symmetric effect, which when this value is negative indicates that the following vehicle is moving slower than the leader. The model tends to predict deceleration and vice versa for positive values. Most importantly, response time is highlighted as a significant predictor for the model. Its position and spread on the plot underscores its role in the timing of a vehicle's response to the leader's action. This again aligns with our research emphasis on incorporating response time into the model, affirming that it is important in accurately predicting autonomous vehicle behavior. The overall takeaway from this slide is clear. By using SHAP values, we can gain a deeper understanding of the model's decision-making process and ensure that it's not only accurate, but also interpretable and hopefully trustworthy. Next slide, please. Continuing with the theme of model explainability, we look at the partial dependence plot to further explain how our models process inputs to make predictions. We focus only on the space headway feature, which was the second feature that was important in the context of the model. The plot that's shown here illustrates the relationship between, again, the space headway and SHAP values. The blue and pink dots represent individual predictions for lower and higher values of space headway, respectively. Two major observations can be made for this plot or from this plot. First, at lower speed headway, that's I think below 30 meter, which indicates closer proximity between vehicles. The model predicts deceleration. Again, this is intuitive and reflects a safety critical response. As vehicles are getting closer to each other, the following vehicle will and is expected to slow down and maintain a safe distance. Second, beyond a certain space headway threshold, the impact of space headway on the model prediction becomes mixed. This suggests that other factors may start to influence the vehicle's behavior more significantly at these greater distances. And the relationship between the space headway and the speed change is not linear, or at least not straightforward. Moving to the next slide. As we draw this presentation to a close, let's go ahead and do a summary of the contributions and findings of this research. First and foremost, this study is among the first in proposing an AV car following model, specifically tailored to mixed traffic conditions. The proposed model stands out for its ability to predict high acceleration and deceleration accurately, addressing a common limitation faced by analytical car following models, which we saw multiple times during this presentation. Furthermore, we found that the leader's acceleration is the most significant trigger for the following vehicle's acceleration response. This insight is crucial for designing AV systems that respond appropriately to the actions of the vehicle ahead. That's because we need to ensure smooth and safe traffic flow. Oppositely, or in contrast, analytical car following models have historically identified a speed difference as the most important trigger for a follower's acceleration. While it's still relevant, this factor alone, we believe, does not capture the full spectrum of variables influencing the AV behavior in mixed traffic scenarios. In conclusion, our work contributes to the body of knowledge with a more nuanced model that offers both better accuracy in prediction and greater relevance to the real-world operating conditions of AV, which is mixed conditions. Next slide, please. Thank you for your attention, and I look forward to any questions and further discussions on this exciting topic. And we can go ahead to the last slide, Dr. Das. We are also acknowledging other co-authors and folks that have been involved in this project, which is Dr. Nagy Raphael, Dr. Billy Williams, and Dr. Dan Harris.
Thanks a lot.
Thank you so much. That was a really great presentation. We enjoyed the very insightful talk on this interesting application of AI to car following problems. So any question? So
yes.
Yeah, go ahead.
I have a question about I think it's in slide 18. So the modification of the deep neural network affect the training result compared to the original one. Like, does it help on increasing the accuracy or converging?
Yes. So to answer that question, like we actually started, we didn't jump to the regularized one in the first place. We started with the normal vanilla LSTM without anything, like the cell structure I just saying. So not only that model had higher RMC, but we also have seen overfitting. Like it was maybe doing good in terms of like the known data, but when it is encountering the unknown data, like the test data or different data set, it was performing really poor. And also the learning rate, the epoch rate was like we have seen from the epoch rate, the learning of the test and like after some time it was not learning the test data. So we actually then understood that we need to modify. We need to add the regularization term because regularization is the most simplified way to counter the work. That's why we just went into work in part and found that the RMAC also increased, and as well as we have solved the problem also at a good level.
Thank you.
Right, thank you. So any other question?
One is, how do you trigger your attention mechanism when you have leader and follower? And what is the duration of this attention that we are talking? Is it in seconds, milliseconds?
That's a great question you asked actually. To go to the attention one. So the data set itself was within the millisecond, like the resolution was 0.1 second. So the attention mechanism that worked with that for the data set also focused on that one. And the second question, the first question that you asked, can you please repeat about the car following scenario? That
question is A, what is the when we apply the attention mechanism? B is how do you trigger this attention mechanism when you have a dynamic situation when both cars are moving?
right. So because we have that observed trajectory data to work with. So what I believe from the attention mechanisms is like they define based on the data set where it has to put the attention, based on changing the weights of the neural nets. So for path epoch, it is changing the weights of the neural nets to fit them on. So normally in normal LSTM models, it put the weights based on a defined equation. But for this one, it is changing because as you can see, it is actually using the softmax function for changing the weights of the mechanism, where on the other LSTM model, it doesn't have anything like that. So based on the data set it is getting from the input get, it is changing the weights for different one based on the complexity. So again, it is all about the learning, whether it is learning from the test and train. So again, the test train curve, based on that, it is defining where it has to put changing the weights of the learning. Does that answer your question?
I will also add, Dr. Humayfar,
Yep.
in a leader-follower model with an attention mechanism, the attention is typically triggered by the changes in speed or distance between the vehicles. So we had both of those available in our data set.
Right.
Yeah, and the mechanism operates in real time, although we had collected this data that was available to us and continuously updates itself with the response time in, as Tanmay mentioned, milliseconds. The data that they collected was, I think, 100 hertz, but then oversampled it to 10 hertz to ensure that there's a timed reaction to the driving environment.
Right.
Okay.
You're muted, Dr. Humayfar, by the way.
How much did it improve your performance?
As Tanmay and I showed, compared to the traditional car following models significantly. However, when we looked at the different flavors of LSTM, obviously the RS-LSTM was doing much better compared to the other ones, but the difference was not that significant. However, compared to the traditional car following models, the analytical ones, it's doing much better job.
Great. Another question that I have was on slide 28 and 31. Your acceleration and deceleration had two, I thought that they are symmetric. But now in 31, it is more symmetric than this one. What is it that you contribute? Why deceleration is not symmetric to acceleration?
The prediction, like the prediction
Yes.
wise.
Yeah. You think that the two should be the mirror or very close to each other. But now, when I look at -4 to -2 and +2 to +4, there's completely two different behavior.
Right. This is governed by the data that we had available. So the x-axis that we see, the ranges for the acceleration is actually what we have in the data set. Unfortunately, the data that we have is not symmetric. I wish it was the case. That way we could have seen how it behaves to both acceleration and deceleration. But this was one of the drawbacks of the data set that we have available.
Yeah.
But if you look at 31, you proposed method.
Let's go to 31.
Yeah, 31. Yeah. You see that this one is, to me, is more symmetric. I don't think it is the data.
Oh, you mean the RMSE values? Why they are not
Yes.
symmetric?
Yeah,
Yes.
yeah, yeah.
Okay.
Yeah, I can jump in.
Go ahead.
So for this one, like as I mentioned, like we have also mentioned it here, like the model that we have proposed here, in fact, like the LSTM model, actually performed better in high deceleration. Though it didn't perform like bad in high acceleration, but obviously it performed well in high deceleration. So that is something, as I mentioned in the slides as well, that we are looking into for future research, and we have some answers that we are actually working on, like why it is happening there. Again, it is based on the data itself. So that is one thing. The learning process and everything, it depends on the data. So as it is governed by the data, we have found that a good amount of chunk of data was on the deceleration portion. It was learning the deceleration portion pretty well, but in the acceleration portion, though it was doing much better than the analytical one, but there is still some room of improvement that we are now currently working on.
And we are also incorporating other data sets.
Right.
Right. Yes.
Yeah. That data set of Vanderbilt, and as well as data set of First Lab from the PATH and the Wisconsin Medicine data, like 3 data sets we are now trying to incorporate to actually solve this issue and some other issues that is based on the contribution of this research as well as the limitations of this.
But I want to appreciate Dr. Onifar. That was really great question of understanding both the physics and also the data that visualization that we are getting, and trying to go beyond the model or try to correlate the model and physics of the system. That was really good question. And I know
I think my question is, I think that it would be nice to look at the density of the vehicle when you are decelerating or when you are accelerating. To me, when you are decelerating, this is just my intuition is telling me that the roads are more dense as compared to acceleration, where maybe it is not as dense as deceleration. Probably, maybe one reason is can attribute to that one. But again, this needs further investigation.
Yeah, and again, that this slide also points out the thing that said, like, you see, these analytical models are, because they have a defined equation, they are performing on both terms symmetric, as you have said right now. Though it was a symmetric model, it is performed in that way. But as it is a learning-based model that we are trying to develop, that is also something. And in fact, we are in the future actually working on to incorporate the analytical model into the learning-based model, like a combination of both that we are trying to now develop. So that is the thing that we are trying to do. Like, we have seen learning-based model cells. We have also seen the cons and pros of the analytical models. So both have some issues. Both have some very good contributions. We are now trying to incorporate both to actually see the to overcome the limitations from both ends. Yeah.
Thank you.
Thanks.
Any other question?
I think we had a question very similar to Dr. Omaifar's question in the chat. I think that's answered, but if it is different than what was asked, please let us know.
Yep.
Very good presentation. Thank you so much.
Thanks a lot. I appreciate your
Sorry, there is one more question.
Yeah,
yes, Dr. Gray, go ahead.
Yeah. Can you hear me? Yeah.
Yes.
Yeah, thank you. It's very interesting research. Thank you, Dr. Das and Dr. Samandar.
If you can talk a little bit louder, we have difficulty to hear.
Yeah.
Oh, okay. Maybe my microphone.
That's better.
Yeah, okay. Yeah, I'll go a little bit closer. Yeah, I have a quick question. So maybe future research. So using L2 regularization, we are penalizing the coefficient that are not important. So it's giving much better result. And let's say, if can we, well, it's your thought. Can we use that L2 regularization with attention mechanism? Basically, attention mechanism focus on like important and unimportant things. Is it possible to combine attention mechanism with L2 that will give much better result?
Definitely it's possible, because if you see, like, the whole idea is to like changing the weights and keeping the weights at a balance. I should say balance because it still is a black box. So that's why I said balance. Now, if you go to the attention mechanism, is again, though neural nets are black box, still it is equations. In very, like, if I go very detail of the neural net. So definitely it is about like rigorous coding and coding from the scratch and changing the equations. So definitely it's possible to do that.
Yeah, and then do you think it will give much better result?
That to research that definitely we are really
both has advantage, so I think it should give some better result.
Definitely, that's a great idea.
Yeah, great suggestion, Dr. Geyer. We'll definitely take a look at that.
Yeah,
and we'll reach out to you if hopefully it gives better response than RS-LSTM alone.
Okay, thank you.
Okay, great. So
I have a question.
Go ahead. We have still time.
Okay. Thank you for the wonderful presentation.
Thanks.
So I was, I think it was on slide 32 where you had the explanation results using SHAP.
Yes.
So was that based on the predictions made by the RS-LSTM model, or which model predictions were used for the explainability analysis?
Dr. Samandar, you can go ahead. You can like.
Sure. Yeah. I think this slide is based on the RS-LSTM.
Yeah.
We did not take a look at the other flavors of LSTM to do a SHAP. Not quite sure if there will be value in it, but that's something that we can take a look at. However, for the second graph where we have in the following page, we just show the PDP for space headway, but we have looked at the other important features as well. And it was part of the IEEE's ITSC conference presentation. Hopefully that proceeding will come out, but we're also planning to submit it to a journal soon. I don't think we will need the SHAP for other models, but if we find that the combination of attention and regularization brings benefits, we will definitely take a look at that one.
Yes, definitely.
Okay. Thank you. Just a follow up. Is there a reason why there's an isolated explainability analysis being done for the space headway feature and not for the other?
I can go ahead with that. So actually, it's not the isolated one because this particular feature, we have other features that we can describe, but because of the time constraint, we didn't include that. First of all, the second of all, we thought that this actually explains the AV piece and as well as car following piece in a whole. So the basic understanding of car following from human perspective is more of like, okay, if the distance between the follower and the leader is increasing, I will accelerate. But autonomous vehicles have some limitations. So in that case, the sensor range. So after a sensor range, the autonomous vehicles cannot actually detect any vehicle in front. Even if you like driving the current ACC equipped vehicles, you'll see after a vehicle is on front, the vehicle is not detecting the front vehicle. So that means at that time, it is not being influenced by the front vehicle at all. So that shows the autonomous vehicles limitations. I shouldn't say limitations, the characteristics of the autonomous vehicle. That's why we just put this slide here. But obviously, we have submitted the whole explainability into the current IEEE conference, right, Shep? And then we are expecting that to be published in the future.
There is a question in the chat box is asking whether, okay, there's a train. Give me 1 second.
Is there a consideration on the traffic behind the AV vehicle?
Yes.
That's a very good question.
It's a very good question, actually.
Yes, it's a very good question. For the purpose of this research, no, we haven't looked at what's behind the autonomous vehicle or what is behind a follower vehicle. But obviously, it becomes important if the vehicles are connected as well. In a context that we have looked at it, it's just when we define autonomous vehicle, it's just the autonomy part. The connectivity part is not there. So the vehicles are not talking to each other. They're not connected. There's no signal transfer between them or message transfer. For this particular research, we haven't looked at that yet, no.
So coming back to the question that Dr. Homeifar asked about the difference between the acceleration and deceleration, is it also could be because during the deceleration and braking, there has been more safety critical sort of systems that are, or different safety mechanisms that might control the behavior of the vehicle compared to acceleration, which might be a little bit sort of more loose control tracking of the speed versus the deceleration and braking, which is more restrict and is perhaps multiple modules might be coming to the become active to make sure that the safe the distance is being respected. Is it possibly partially explain the problem?
Well,
go ahead, sir. Go ahead, sir. Then I can. Okay.
So yeah, I think that's the case for when the designers or MOEs of these AV systems design the vehicles, in their mind, the number one priority is safety. Especially if they get in a condition or situation where they have to brake, they have to do that, right? That's the priority. They give priority to the safety. I feel like that's the case, but we haven't been able to show that explicitly from the data set that we have available. Correct me if I'm wrong here, but we haven't looked into that from the real world collected data that we have access to.
In fact, to just like what Dr. Ali and Samandar just now said, that deceleration is pretty defined. Whenever there is a safety critical situation, the pattern is easy to learn for the learning algorithm. But acceleration, even if you see from this graph, the acceleration piece, it is accelerating at different scenarios, but the deceleration piece is pretty determined that which scenarios actually define deceleration. So for the learning algorithms, it is also, so it is actually what it's doing. It is learning the sequences, right? So the learning algorithm is actually learning those sequences in the deceleration process better than the acceleration. Acceleration is itself a bit heterogeneous in terms of like behavior. So that's is also one of the case, which actually relay what you just now said, Dr. Ali, that the mechanism of the autonomous vehicles. Now, again, I am going back. I really like this comparison of the graph, and I didn't look into the way I am looking at right now, the symmetric part. And as we have said that the future research that we are currently doing right now is actually the incorporation of the analytical model with the neural nets to actually take the advantage of both, so that we can actually mitigate these limitations, and as well as the idea that we have got right now today, like putting the regularization term into the attention mechanism to find. I think that can also, this to work, definitely I'm hoping to improve this whole scenario a lot.
So I think even if we go with that justification, still then we fix one result, explanation of one result, but then the question comes back, why is it not the case for this particular slide 31, right? So perhaps there are some other factors that has to be taken into account because as you mentioned, there might be, I mean, it's not just acceleration and deceleration. There might be some other factors that, for example, speed at the time of deceleration, or let's say the distance at the time of deceleration, or those sort of things that might trigger different braking behaviors and that might create different behaviors that you can see here. That's something that might be relevant here.
Sure.
So any other question?
Ali, that's a good point, actually. Do you, off the top of your head, and not to put you in the spot, think any other features that we could get from the data set that we have available that could help out with that? I know you were thinking of, okay, what other features you have available, and if you include those, would that probably take care of the asymmetry?
I think one of the Jose Matud, who is a postdoc in our team, might have a little bit better insight into that. He was working on the sort of safety frameworks that he has been working. That's one thing. And then the other thing, there was another researcher that we had another talk a few months ago in the same the sort of almost similar topic. I can share that call as well. But Jose, if you are in that in here, do you have any insight here? Okay, maybe we can set it up conversation and we'll convey the question and then we'll follow up by email later.
Sounds good. Thank you.
Okay.
Great. Shoaib, do you think, Shoaib? No?
Yes, we can hear you.
Yes, I can hear you, Dr. Omaifa.
Do you think you can share the data set that you have with
Absolutely.
our
Yes, definitely. We can share that.
or it would be very nice that if you could share a paragraph about the features of your data set. Because
Yes.
now I can tell you that our group has been working with the Honda data set right now. It's really nice. But now since you have this data set, sharing this data set with the group, it will facilitate on, getting papers out real fast. And then even opens up to collaboration.
Definitely, we can do that. We can share the link to the data set as well as a paragraph or two that talks about the features that we used for training the models.
Absolutely.
Thank you.
Okay. Great. It is now 4:05, and thank you everybody for attending this meeting, and thank you to speakers today. It was very informative talk, and plus a very informative conversation, and that's something that we love to have here, and we appreciate everybody participating in this conversation. And let's please join me to thank the speakers today, and thank you so much, and everybody, hope you enjoy your weekend.
Thank you
So much.
Thank you, everyone. Enjoy your weekend.
Enjoy.
Bye-bye.
Thanks.
Bye.
Thank you.